So this session we will find the little x, the real number that is not mapped to by the function f that maps the set of positive integers to the set of reals. So this, we're assuming by proof by contradiction. So we're assuming the opposite of what we're really trying to prove, and that opposite is that there is a bijection between n and r. So to get a contradiction, we will try to find this real number, call it x, that is not mapped to. So there's just no positive integer that maps to it. So that's the objective, and we'll use the diagonalization method to do it. So this session boils down to, well, how do you do that? Right? So how to do that? Well, I think instead of going this way, it's a bit woolly. I'll start it in a concrete way. Imagine there really is a function f that maps the positive integers n here, 1, 2, 3, 4, and this function maps that positive integer into a real number. Okay, so for example, here's a table of the mapping. There'll be an infinite table, of course, because both the integers and the reals are infinite sets. Okay? So it just goes down infinitely. So let's assume this function f exists. So it'll map, let's say, 1 to, well, this number is pi. You may recognize that number, 3.14159 ... Okay, and it maps 2 to this real number, it maps 3 to that real number, it maps 4 to that real number, and so on. So just assume there is such a mapping. There is a bijection, correspondence, Sipser's term, between the positive integers, the countable numbers in other words, and the reals. This f of n are the reals. These are all real numbers. Okay? Now the trick is, we're trying to find an x, also a real number, but is not mapped to by any of these n's. And how do you do that? Well, you construct this real number, call it little x, that is different from every real number in this list. Okay? How do you do that? Well, you have a look at the, for 1 here, you have a look at the first decimal digit to the right of the decimal point, and you choose another digit that's different from it. Now in this case it's 1, so choose, I don't know, what do we say? Let's keep it the same as the notes. 4. Okay, just choose some other digit that's not the same as that one. Here it's 1. Okay, so choose just some other one. You've got 9 choices. Well, let's just randomly choose 4. Right? So our x that we're forming, let's assume its value is between 0 and 1. So it's right. So the first digit after the decimal point for little x will be 4. So far we've got 0.4 ... So we'll keep filling out the dots. Right? So by making it 4, having the first decimal digit being 4, that means that x is not equal to this. Can't be. Right? Because the first decimal digit of x is 4, whereas this one, the first decimal digit, is 1. Okay? Maybe you're already starting to see where I'm going with this. Alright, let's do something similar with the second number, the second real. Well, in this case it's 55.555. Now the second decimal digit is 5. So let's make the second decimal digit in x a a digit that's different from 5, different from this second one. Okay, what do we call it? 1. 6. And of course 6. Okay, 6 is different from 5. So now our little x has the value 0.46 ... And 0.46 can't be the same as this because we have a 4 where this has a 1. And it can't be the same as the second one because we have a 6 in the second decimal digit, which is different from what this one is, which is 5 here at the second decimal digit. And then we look at the third real number. It corresponds to the positive integer 3, and its third decimal digit is 3. So we'll just choose something different. Let's say 4. Okay. So our x now is 0.464 ... And that x can't be the same as this because it's different from this first position digit, and it can't be the same as the second one because it's different from the second position digit here. It can't be the same as the third one because it's different from, with the third position digit here, and so on. Now you just keep doing that. Now can you see you're going down this diagonal? In the first case, hence the label of the method, diagonalization method. So you look at, so if you're down here at the ith positive integer, well then you'd look at the ith decimal digit in the real, and your x, the ith decimal digit in your little x would be different from the ith digit in your ith real. I hope you follow that. If you don't, rewind. Okay. So you just go down this diagonal and you just putting in for your value of x at the ith decimal digit a value that's different from the corresponding ith real number at the ith decimal digit of the ith real number. And so your x will differ from every, if you keep doing that infinitely, then your x will differ from all of these reals in this table. Okay? That's the essential idea. That's the core idea of this proof of the diagonalization method. It was a work of genius on the part of Cantor. Right? Therefore, you have constructed a little x that is a real, obviously, because it's just a infinite sequence of decimal digits, and it's been constructed in such a way that it is not equal to any of these. Okay, and therefore it's a real that does not belong to this list. Doesn't belong to the list. Okay, it's a real, but it is not mapped to. Doesn't belong to this list. If it did belong to the list, there would be some integer n that mapped to it. But we've constructed an x that does not get mapped to, right? Because it's not in this list. Okay? So that's the essence of the proof. So here's our growing, increasingly specified, if you like, our little x, this real number we're constructing. So 4.641 ... and just keep, you go down the diagonal. I put these sort of double bars under here. That was the first decimal digit, and that was the second decimal digit, that was the third, that was the fourth, and so on. So you're sort of going down diagonally and constructing your x digits that differ each time at each position, at each digit in your X, that differ from the corresponding number at each line in this table. And this table is assumed to be the table that corresponds to F. It's the mapping table, if you like, that maps the positive integers into the reals. Now, there's a bit of a, I don't debate whether to put this in or not. It's a bit of a complication. There might be a slight problem. For example, when you're talking about infinite real numbers with an infinite number of digits, then 0.1999, dot dot dot, they're all nines then, and 0.2000 dot 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 dot, they're all dot dot dot, they're all zeros. They're actually equal, so you might have a bit of a problem then. So they're equal in size, in value, but their decimal representations are different. When you see this is, you've got a 2 here, you've got a 1 here, and so on. So the way they're represented as decimals is different. Okay, but they do have the same value. Now you can avoid that problem. You can go around the problem simply by when you create your X, you choose not to use 0 or 9. If you think about it, that will allow you to go around the problem. You just avoid this issue. It's a bit of a complication, but tossed in there for. Right. Well, that's so we've effectively proven the diagonalization method works for showing that big R, set of real numbers, is not countable. Okay. We've proved it by contradiction. We've found a real number that is not mapped to, and therefore that mapping is not onto, and therefore it's not bijective, it's not a correspondence, and therefore there is not a correspondence or a bijection between the reals and the natural numbers, and therefore, by definition, the set of reals is uncountable. Remember, countable means there is a bijection between the n and the set, and uncountable means, by definition, that there is not a bijection between n and the infinite set you're talking about. Okay, so we've proven that big R, set of real numbers, is not countable. It is uncountable.